I promised you that I'd give you some more Pythagorean theorem problems, so I will now give you some more Pythagorean theorem problems. And once again, this is all about practice. Let's say I had a triangle. Let's say it is, let me just draw my right triangle. Oh, that's an ugly looking right triangle. Let me draw another one. There, I just drew you an equally ugly looking right triangle. And if I were to tell you that this side is 7, this side is 6, and I want to figure out this side. Well, we learned in the last presentation, which of these sides is the hypotenuse? Well, here's the right angle, so the side opposite the right angle is the hypotenuse. So what we want to do is actually figure out the hypotenuse. So we know that 6 squared plus 7 squared is equal to the hypotenuse squared, and in the Pythagorean theorem they use c to represent the hypotenuse, so we'll use c here as well. Is equal to c squared, so we'll say c equals the length of the hypotenuse. And 36 plus 49 is equal to c squared. What's 36 plus 49? It's 70, it's 85. 85 is equal to c squared. Or c is equal to the square root of 85. And this is the part that most people have trouble with, is actually simplifying the radical. So, let's see, the square root of 85. Can I factor 85 so it's a product of a perfect square and another number? Let's see, 85 isn't divisible by 4, so it won't be divisible by 16 or any of the multiples of 4. Let's see, if it's divisible by, 85, 5 goes into 85 how many times? It goes into it, no, that's not a perfect square either. I don't think 85 can be factored further as a product of a perfect square and another number. So, you might correct me, I might be wrong, this might be a good exercise for you to do later, but as far as I can tell, we have gotten our answer. The answer here is the square root of 85. And if we actually wanted to estimate what that is, well, let's think about it. The square root of 81 is 9, and the square root of 100 is 10, so it's someplace in between 9 and 10, and it's probably a little bit closer to 9, so it's 9 point something, something, something. And that's a good reality check. That makes sense. If this side is 6, this side is 7, 9 point something, something, something makes sense for the side, that length. Let me give you another problem. Let's say that this is 10, and this is 3. What is this side? First, let's identify our hypotenuse. Well, we have our right angle here, so the side opposite the right angle is the hypotenuse, and it's also the longest side. So it's 10. So 10 squared is equal to the sum of the squares of the other two sides, is equal to 3 squared, and let's just call this a, pick it arbitrarily, plus a squared. Well, this is 100, is equal to 9 plus a squared, or a squared is equal to, 100 minus 9. A squared is equal to 91. So a is equal to the square root of 91. And I don't think that can be simplified further either. See, 3 doesn't go into it. I wonder, is 91 a prime number? I'm not sure. As far as I know, we're done with this problem. Let me give you another problem. And actually, this time I'm going to include one extra step just to confuse you, because I think you're getting this a little bit too easily. Let's say I have a triangle. And once again, we're dealing all with right triangles now. And never even attempt to use the Pythagorean theorem unless you know for a fact that it's a right triangle. But in this example, we know that this is a right triangle. If I were to tell you the length of this side is 5, and if I were to tell you that this angle is 45 degrees, can we figure out the other two sides of this triangle? Well, we can't use the Pythagorean theorem directly, because the Pythagorean theorem tells us that if we have a right triangle and we know two of the sides, that we can figure out the third side. Here we have a right triangle, and we only know one of the sides, so we can't figure out the other two just yet. But maybe we could use this extra information right here, this 45 degrees, to figure out another side, and then we'd be able to use the Pythagorean theorem. Well, we know that the angles in a triangle add up to 180 degrees. Hopefully you know that the angles in a triangle add up to 180 degrees. If you don't, it's my fault because I haven't taught you that already. So let's figure out what the angles of this triangle add up to. Well, I mean, we know they add up to 180. But using that information, we could figure out what this angle is. Right? Because we know this angle is 90, this angle is 45. So we say 45, let's call this angle x. I'm trying to make it messy. Okay. 45 plus 90, right? This just symbolizes this is a 90 degree angle, plus x is equal to 180 degrees. And that's because the angles in a triangle always add up to 180 degrees. So if we just solve for x, we get 135, that's a 5, plus x is equal to 180. Subtract 135 from both sides, we get x is equal to 45 degrees. Interesting. X is also 45 degrees. So we have a 90 degree angle and two 45 degree angles. Now I'm going to give you another theorem that's not named after the head of a religion or the founder of religion. I actually don't think this theorem has a name at all. But it's the fact that if I have a triangle, I'm going to draw another triangle out here, where two of the base angles are the same. And when I say a base angle, I just mean two angles. If these two angles are the same, let's call it A. They're both A. Then the sides that they don't share, right? These angles share this side, right? But if we look at the sides that they don't share, we know that these sides are equal. I forgot what we call this in geometry class. Maybe I'll look it up in another presentation. I'll let you know. But I got this far without knowing what the name of the theorem is. But and it makes sense. You don't even need me to tell you that. How could I draw this angle? If I were to change one of these angles, the length would also change. Or another way to think about it, the only way, I don't want to confuse you too much, but you can visually see that if these two sides are the same, then these two angles are going to be the same. If you changed one of these sides' lengths, then the angles will also change, or the angles will not be equal anymore. But I'll leave you that. I'll leave that for you to think about. But just take my word for it right now that if two angles in a triangle are equivalent, then the sides that they don't share are also equal in length, right? So make sure you remember, not the side that they share, because that can't be equal to anything. It's the side that they don't share are equal in length. So here we have an example where we have two equal angles. They're both 45 degrees. So that means that the sides that they don't share, this is the side they share, right? Both angles share this side. So that means that the side that they don't share are equal. So this side is equal to this side. And I think you might be experiencing an aha moment right now. Well, if this side is equal to this side, I gave you at the beginning of this problem that this side is equal to 5. So then we know that this side is equal to 5. And now we can do the Pythagorean theorem. We know this is the hypotenuse, right? Hypotenuse. So we could say 5 squared plus 5 squared is equal to, let's say c squared, where c is the length of the hypotenuse. Well, 5 squared plus 5 squared, that's just 50, is equal to c squared. And then we get c is equal to the square root of 50. And 50 is 2 times 25, so c is equal to 5 square root of 2. Interesting. So I think I might have given you a lot of information there. If you get confused, maybe you want to rewatch this video. But on the next video, I'm actually going to give you more information about this type of triangle, which is actually a very common type of triangle you'll see in geometry and trigonometry, called a 45-45-90 triangle. And it makes sense why it's called that, because it has 45 degrees, and a 90 degree angle. And I'll actually show you a quick way of using that information, that it is a 45-45-90 degree triangle, to figure out the sides if you're given even one of the sides. I hope I haven't confused you too much, and I look forward to seeing you in the next presentation. See you later.